Alright, grade 10s. Today what we're going to do is physical sciences, of course, but the physics component of it, we're going to be having a look at electrostatics, okay, which forms part of the physics section for term 1, 2021. And electrostatics, we're going to open up by looking at positive and negative charges. Okay. So, we're going to try and summarize as much as possible with still getting all the important information across. Okay, so electrostatics. Okay, we're going to have a look here quickly. Electric charge, alright, something called electric charge is what is known as a property of a particle. Okay, let's get that down. There are two types of charges that exist. Positive, alright, and negative, but more specifically two types of electric charges. Okay, there's positive electric charge and there's negative electric charge. Okay, we have discussed this in our previous section. Okay, all matter is made of atoms, all right, and an atom consists of a positively charged nucleus surrounded by negatively charged electrons. Okay, in our section where we dealt with the atom and we dealt with the classification of matter, we had a look at that. Okay, now what exists in the nucleus? All right, the nucleus exists of neutrons and protons. Okay, where we know that neutrons are what's the word I'm looking for? Neutral. They're neutral in charge. Okay, they're very neutral particles, and where protons are positively charged. Okay, so let's maybe put that down. Okay, that protons, just as a refresher, they are positive or positively charged. Okay, and then of course we have electrons, okay, which are negatively charged. Okay, negatively charged. These quotation marks mean the same word down there. Okay. Is if we ask the question, what's the difference between a proton and an electron, and that answer is almost nothing. Almost nothing. There is something that separates the difference. Okay, because numerically, right? Numerically, all right, they have the same value, or they can have the same value. Okay, what is the difference? Okay, the sign. The one is positive and the one is negative, but numerically they can have the same value or the same charge. Okay, so what's a charge in an electron? All right, if I have a look in my table of constants, all right, it has a value of negative 1,6 times 10 to the negative 19. All right, I just need to check the forgot the oh, of course, I remembered it now. Coulombs, okay, and proton is just positive. Okay, that's all difference, but numerically they have the same value. Numerically same. Okay, just the sign's different. The next point is that we obviously know the different values of a proton and an electron, but rather that in a neutral atom, okay, obviously we have mentioned what a neutral atom is, okay, but in a neutral atom, okay, the number of, okay, I'll shorten the numbers to NO, the number of electrons, okay, is equal to the number of protons. Okay, it's equal. So the atom actually has no net charge. Okay, so therefore no net charge or overall charge. Okay, it's nothing. Okay, protons and electrons equal each other. For example, if we even had to use a mathematical sum, so we have electrons minus 1,6 times 10 to the negative 19, alright, plus, which is protons value, 1,6 times 10 to the negative 19. What do you get? Negative value plus the positive of the same numerical value gives you 0. Okay, so no net charge. Okay, protons and electrons equal to each other. Okay, that proves my point there. However, if an atom, okay, loses, okay, one or more electrons, okay, if it loses one or more electrons, okay, or gains, okay, extra electrons. So it can either lose one or more, or it can gain, alright, extra electrons. Okay. Obviously, the number of protons, okay, does not balance. There's imbalance. Okay, so they don't balance each other out. And who's each other? The protons and the electrons do not balance. So we don't have this scenario up top here. Okay, there's now an imbalance. Okay, therefore, what does this result in? It results in an atom, therefore, being charged. Okay, and we call, different color, a charged atom, okay, is called an ion. Okay, not iron, but an ion. Okay, this does exist even in physics as it does in chemistry. Okay, so now, just to say that point again, an atom can lose electrons, it can lose one, it can lose more than one, it can also gain. Okay, doesn't matter what it does, but there will be an imbalance of protons and electrons, or protons versus electrons. The atom will therefore appear charged, and if it appears charged, a charged atom now is called an ion and no longer an atom. Alright. Now, the question probably on everybody's mind, what happens if an ion has more electrons than protons? Okay, so what happens, okay, in this situation? Okay, where we have more electrons. Okay, we'll use a mathematical operator here than protons. Okay, let's maybe change this sign here. Let's maybe use something a bit better. Let's maybe use that. Cool. So there's more electrons than protons. Okay, so that means it has a negative charge because there's more negative electrons. All right, electrons are negative, so there's more negative than positive, so it has a negative charge. Okay, so if your electrons are more than your protons, you'll have a negatively charged. But of course, if the opposite is true, in other words, let's write that a bit better. If, of course, there are fewer electrons than protons, or more protons than electrons, you will have a positively charged ion. Does that make sense? Now, we've been speaking a lot about positively charged and negatively charged and understanding how they all happen. But the next question is, what happens when we bring two objects together? Okay, very interesting question. Okay, now of course, when two objects come into contact, okay, so if I have two objects, right, and they come into contact, okay, there is something that is called a transfer. Okay, there's something that's called a transfer of electrons. Okay, or might not be a transfer of electrons, or more specifically, sorry, I'm talking a bit of rubbish. Okay, electrons are able to freely go between two objects. They are able to move, right? They can go ba ba ba. Okay, so when two objects are brought into contact with each other, such as a ruler and your hair, okay, there's a transfer of electrons that takes place. Okay, so when there's a transfer of electrons from one object to another, okay, what does it cause? It causes both objects to become charged. Okay, causes both objects, both is not spelled with the E, to become charged. Okay, so that's what happens. Alright, that's what happens. So, the ruler and the hair is a very a good example. I tried this at school. If you use one of those like shatterproof rulers and you just rub it on your head for, I don't know, maybe 5 seconds, you'll be able to the paper on your page in your book will be attracted to your ruler, right? Almost like a magnet. Okay, because there's a charge, of course, exchange or a charge transfer that happens from your hair to the ruler, and then vice versa. Okay, one object becomes more positively charged once it loses electrons, and one object becomes more negatively charged as it gains electrons. Okay, and that's how that whole process works. So, forces of repulsion and attraction, like magnets, quite similar. Okay, like charges, okay, what do? They repel. Okay, unlike charges, of course, they would attract. Okay, they will attract. Okay, attract each other. Okay, if we move, all right, to also what we discussed, also when we were busy with chemistry, okay, we had a look at conductors. All right, so diving more into the physical properties. Okay, if we have conductors, first of all, we know that they are materials. Okay, number one, but conductors have what is known or what is called mobile charged particles. In other words, these particles are free to move. They are free to move around the material and also free to be transferred, all right, from one material to another. Okay, that's why we say conductors are very good at allowing electricity to flow through them. All right, they can conduct the electric charge very well. But then, of course, we have the opposite, which is our insulators. Okay, now insulators, of course, they have no mobile. Okay, no mobile charge particles. That's why they are not very good, or they cannot allow electricity or electric charge rather to flow through them. Okay, they suck at it. Okay, they cannot conduct. All right, how does charging happen? Charging by contact, all right, or rubbing, all right, is a method for charging two insulators. Okay, provided that they are of different materials. Okay, objects of the same material cannot be charged by contact. Okay, so you see we have a ruler. A ruler would be an insulator. Okay, nothing can flow through there, obviously, because of the property of the material. Okay, but obviously we rub it on our head, right, with our hair. Okay, they are two different. Okay, hair cannot charge hair. Ruler cannot charge another ruler. Okay, but two different materials of insulator, we can charge them. Okay. There is something that exists that is called the triboelectric series. Triboelectric series. Now, what does this do? This helps us work out the type of charge, positive or negative, on two materials that have been charged by contact. Okay. Okay, so let's just summarize that quickly. Okay, they help us work out type of charge, okay, which is obviously either positive or negative. Okay, so obviously on the triboelectric series we have a more positive end of the series to a more negative end of the series. So starting from human hands, they are up top there, or they are at the top of the positive end, human hands, and at the bottom would be the silicone rubber. Alright, cool. Don't worry about this. I'll get that little screenshot of the triboelectric series table to you, to the class, so don't worry about it. Okay, but it's also very common. You can find it on the internet as well. It's just a list. Okay, obviously we'll determine the type of charge. Okay, more positive, and as we keep going down, we get more negative. Okay. Almost everything in physical sciences leading up from grade 10 all the way through the matric exists because there's a law in place. Okay, science is almost based entirely on law. Okay, nothing is outside of law. Okay, law is only there to maintain order. Okay, same thing here. Okay, the law of conservation of charge, what does it state? It states that the net charge, or the overall charge, okay, of an isolated system remains constant during any physical process. So what does that mean? It means that it's in an isolated environment. Anything that's in an isolated system or isolated environment, okay, means there are no external factors that can interfere with our little experiment or reaction that is about to go down. Okay, so that means the net charge or total or overall charge of an isolated system that will always remain constant or conserved during any physical process, of course, in an isolated system. The law also means that electric charge cannot be created or destroyed. Okay, like energy, it cannot be created or destroyed, or that the net charge produced on any process is zero. Okay, so charge cannot be created or destroyed. Okay, electric charge. Okay, neither can the net charge produced during any physical process be equal to zero, right? It just cannot happen. Okay, that's what the law also states. Okay, now we're going to introduce a formula, and that formula basically is going to represent what happens when we have two identical charged conductors. Okay, so we have two conductors. Okay, let me just put a dot there. A dot here. So we have two, we can say identical. Yes, they don't have to not be identical. Identically charged conductors, and we're going to use the symbol for charge, okay, which is Q. So let's say I have Q1, which is conductor 1 that is charged, and I have Q2. Okay, Q meaning charge. It's the symbol. Okay, it's not what it's measured in. Charge is not measured in Q. No, but whenever you see Q, you know we're talking about a charged object. Okay. What happens if they are brought into contact and then separated? Each conductor will have a charge after separation. Okay, and we introduce a formula called Q. The charge on two identical conductors that have been brought into contact and then separated will be the charge on the one plus the charge of the two divided by 2. And then we will have the charge on both, because they've been brought into contact and then they've been separated. So 1 plus the other divided by 2. The divided by 2 shows the separation. Now they'll have the same or identical numerical value of charge on both. Okay, They will share the total available charge equally, in other words. Okay. Now, this principle of the law of conservation of charge only applies when referring to identical conductors, okay, of equal size, okay, and they are obviously insulated from their surroundings. So in other words, there's no other external force or anything else interfering with them. Okay, they must be identical and they must be conductors of equal size. Okay, metal spheres, same material, identical, two of them, equal size. This law obviously exists. So with charge quantization, okay, the SI unit, okay, of charge is coulomb. Okay, it's measured in coulombs. Okay, and we use the symbol C. Okay, just C. Okay, so for example, earlier, charge on electron -1,6 times 10 to the -19 coulombs, C. Okay. 1 coulomb is a large quantity of charge. Okay. We produce typical charges of about, if I just write that, typical charges. So if you have 1 coulomb of charge, that's quite a lot, okay? But typical charges that are produced is less, is equal to about 10 to the -7 coulombs. All right, we would charge objects by contact or by rubbing. Okay, so if you have 10 to the -7, that's also about the same thing as 1 over 10 to the 7. Okay, so it's quite a small number. Okay, so if you have 1 coulomb of charge, that's a lot of charge. Okay, that's a lot of charge. 1. For this reason, we often make use of something that's called the microcoulomb. Okay, microcoulomb. And we also make use of something that's called the nanocoulomb. Okay, now microcoulomb is used the Greek symbol, which is mu, right, which is a funny looking U, right, and capital C. And nano, we make use of the N, little n, capital C. Okay, but these mean different things. So microcoulomb is basically 1 over 10 to the 6 coulombs, or more typically written 10 to the -6 coulombs. Okay, so if you see a microcoulomb, you know it's times 10 to the -6. Whenever you see a nanocoulomb, it's 1 over 10 to the 9 coulombs, or 10 to the -9 coulombs. Okay, and it's typically written like in these two forms because of scientific notation. Okay, the same way, look here, we don't say 1,6 over or 1,6 times 1 over 10 to the 19, but rather 1,6 times 10 to the -19. Okay, that's how we write it. Okay, and this is obviously the charge on a single electron. I must put this in there. It's a charge on a single electron. Okay, now the electron obviously is an elementary particle. It does not consist of smaller particles, right? Because we know, again, what an element is. It's the simplest, all right? Smallest as well. You don't get anything smaller than it. So its charge is the smallest charge in nature that does exist. All right. The value of 1,6 times 10 to the -19 coulombs is what is called a fundamental constant. It'll be on the table of constants. Okay. Objects cannot gain or lose a fraction of an electron. Okay. So the net charge Q on an object is an integer. Okay. And we obviously introduced this formula called Q is equal to NE. Okay, in other words, what happens here is objects, again, they cannot gain or lose a fraction. They gain an electron or they lose an electron. So net charge Q on any object is an integer or multiple of E, which is what electron is, okay, or elementary charge. Okay, so N is going to equal 1, 2, 3. So the number of electrons, or number of electrons lost or gained, of course, and you want to find out the charge. Okay, this E doesn't have a minus on top of it, sorry girls. Okay, and E would be the elementary charge. Okay, sometimes it's also denoted as in Q. Alright, I think, yeah, in Q, might be proved wrong here. Yeah, there you go. In Q. Okay, it disappeared now, but anyway, I texted it there. Cool. This is obviously of our NTP. Okay, whichever one, it doesn't really matter. Okay. The electric charge is quantized, meaning it exits only in discrete quantities, multiples of 1,6 times 10 to the negative 19, and we'll look at that a little bit more in a couple of exercises that I'm going to showcase for you in just a moment. Okay, so take a screenshot of that if you need to, okay, and we'll practice. I just need to find the booklet that obviously has the electrostatics part in it. The booklet that I found had only electromagnetism in it, but it had everything that we had done in term 1 with the atom and everything. So just give me one moment. So in this first little activity we're going to do, just to have a look at what we just discussed today so far, is in this little worksheet here, number 1, it says choose correct answer A, B, C, or D for questions 1 and 2. Okay, we're just looking at question 1 for now. A plastic rod and a dry cloth are uncharged. The plastic rod is rubbed with the dry cloth and they both become charged, and the rod becomes negatively charged because some particles move from the cloth to the rod. What is the charge on the cloth and which particles moved in the charging process? So we've got A, positive, B also positive, but A is charge on rod was positive and particles that moved were the protons. B, the charge on rod was also positive, the particles that moved was electrons. C, the charge on the rod was negative and the particles that moved were the protons. And D, the charge on the rod was negative and the particles that moved were the electrons. Alright, we need to choose the correct answer. So, how we answer this question is not very difficult. It's not very difficult to understand or to grasp, alright, initially, because they say yes, they both become charged, but the interesting part that we need to pay attention to of this question is it says the rod becomes negatively charged because some particles moved from the cloth to the rod. So if something becomes negative, alright, if it becomes negative, alright, it must have gained some type of negativity. So I'm just giving that as a hint to answer the first question. The answer for that one, ladies and gentlemen, was B. Okay, the charge on the rod, alright, becomes positive, alright, and the particles that moved were the charge on the rod was positive, and the particles that moved were electrons. Okay, so the cloth would become positively charged because most of the electrons, or there was an electron transfer from the cloth to the rod becoming negatively charged, and the protons becoming and the cloth becoming more positively charged. If you look at number 2, a positively charged plastic rod attracts small pieces of paper, almost similar to the ruler and the hair, because if you rub the ruler on your hair and then you put it on your page of your book will be attracted to the ruler. So similarly so. Okay, the positively charged plastic rod attracts small pieces of paper because A, the paper pieces are negatively charged, B, the paper pieces are neutral, C, the paper pieces are very small, and D, the paper pieces become polarized. Okay, have a little bit. With your answer, we found there was D, the pieces of paper become polarized. Okay, it's because positively charged rod will attract or attracts the negatively charged electrons in the paper pieces, causing the molecules inside the paper to become polarized. Okay, then the negative parts of the molecules are attracted, therefore, to the rod. Something interesting to note, though, about options B and C. Options B and C are true. Okay, I can't remember what they are right now, but they are true because in each of them, it is not the reason. It's not the reason why the paper pieces are attracted to the rod. Therefore, they are incorrect. So they are true within themselves. They are small and what have you, or they are neutral or what have you. I think those are the two options there. But those are not the reasons why they are attracted to the rod. They are attracted to the rod because the positive charge rod attracts the negative charge electrons on the paper pieces or in the paper pieces, and that causes the molecules inside the paper to become polarized, and that's why they are attracted to the rod or ruler. Alright, question 4 is a nice question. Question 4, okay. Question 4, two identical pith balls are suspended on a light inelastic cotton threads. Pith ball A has a positive charge of 5,4 nanocoulombs, while pith ball B carries a negative charge of 8,2 nanocoulombs. State the principle of quantization of charge. Okay, the principle of quantization of charge. 4.2, calculate the extra number of electrons added to the pith ball B. Okay. 4.3 is describe the type of force that pith ball B exerts of pith ball A. I would say rather on pith ball A. Okay, I'll go with it. And then 4.3 goes on to say the pith balls are brought up together and then they are separated again to hang at the same original distance apart. 4.4 says state the law of conservation of charge. And then 4.5 says now use the law to calculate the charge on pith ball B after it has touched the pith ball A, then separated. How many electrons were transferred from pith ball B to pith ball A when they touched each other? It's quite a nice little question for question 4, so we're going to spend some time doing it before we go through the solutions. So what I want to do, ladies, is just start with answering 4.1's question, which was state the law for quantization of charge. Okay, and that basically in one line is saying that every charge in the universe consists of integer multiples of the electron charge. Okay, that's all it is. Okay, every charge in the universe consists of integer multiples of the electron charge. Okay, obviously integer being 0, 1, 2, 3, etc., etc. Those are just integers. Okay, all integers. We all understand what an integer is. In grade 8 maths, we learned what an integer was. Okay, same thing. Cool. Now for 4.2, okay, this is my little drawing here, of course. One sphere is positive, and one sphere or ball is negative. Okay. Of course, we have our formula Q equals NQ or NE, whichever one, doesn't really matter. Okay, so Q, we're told, -8,2 times 10 to the -9 equals N, because they want to know the number. Alright? They want to know the number, okay, of electrons. Alright? With the difference. Okay, the number of electrons that was added to ball B. Okay, Q is obviously the charge on an electron. So what we have to do, we have to divide both sides by the charge on an electron, which is -1,6 times 10 to the -19. Alright. So obviously here they cancel each other out, okay, and here of course we have a sum that we can put into our calculator. Okay, so in our calculator we type the fraction options, -8,2 times 10 to the -9, all divided by -1,6 times 10 to the negative 19. And you're welcome to use brackets, of course. Brackets just neaten everything. Just putting my brackets in quickly. Cool. And the answer that we get for n is equal to 5,125 times 10 to the 10. Right? Remember, it is an integer. For 4.5, they do ask us to use the law of conservation of charge to calculate the charge on ball B after it has touched ball A and is separated, of course. So we bring out the formula. Q is equal to Q1 plus Q2 all divided by 2. So we have 5,4 plus negative 8,2. And we're going to divide that by 2. Okay, so we just plug that in on our calculator. 5.4 plus negative 8.2 all divided by 2, and we get an answer of minus 1,4. Of course, it's my bad. I forgot to add in the 10 times. Just put nanocoulombs there. I forgot to add in the times 10 to the negative 9 because it was with nanocoulombs. How foolish of me. Okay, so just use that, nanocoulombs. Okay, times 10 to the negative 9. And the same thing here on this one, times 10 to the negative 9. And obviously we get negative 1,4 nanocoulombs times 10 to the negative 9 coulombs. Okay, that is our answer there. Okay. And then in 4.6, how many electrons were transferred? All right, after they touched each other. So for 4.6, we use the same formula. We use Q is equal, same formula as in 4.2. In Q, so this is obviously our Q. So negative 1,4 times 10 to the negative 9 is equal to N times negative 1,6 times 10 to the negative 19. Okay, so we divide both sides by this number. They cancel. Negative 1,6 times 10 to the negative 19. And therefore the N, in this case, is going to be equal to, just give me one moment, 1,4 times negative 9 times 10, negative 19. Well, I've got to now use scientific notation now. Okay, so just to divert you back to 4.2, 4.2 was calculate the number of extra electrons. I almost invented a new word, extrons, for extra electrons. Anyway, was added to ball B. We calculated that to be 5,125 times 10, 5,125 times 10 to the 10. And 4.6 is now how many electrons were transferred from ball B to ball A when the balls touch together. So we calculated during that was 8,75 times 10 to the 9. So what we have to do is take the extra number of electrons that was added to ball B, which was 5,125 times 10 to the 10, and minus the amount of electrons that was transferred, which is 8,75 times 10 to the 9. And once we do that, we'll get an answer. So 5,125 times 10 to the 10. Okay, minus 8,75 times 10 to the 9. And we get an answer of 4,25 times 10 to the 10. Number of electrons was transferred when ball B touched ball A. And that concludes my presentation for this week on electrostatics. Please stay tuned for the next video where we have a look at the next topic of electric circuits.